Hello again to the third part of our series in medical device electrical safety. So today we're going to go over electrical current, and what I mean by that, the different factors that affect electrical current when it's non-invasively applied to the skin of our bodies. And there's four factors that affect how electrical current, the severity of the physiological effect from electrical current. So I'm going to go over four factors in this video, but in the next video I'm splitting this into two parts. The first one is going to talk about the different factors, and the second part of this section will be discussing the macroshock, microshock, and the different types of pathways leakage current can flow. So as you can see from the screen, there's four different factors that could affect the electrical current in the human body. So the first one is the intensity of the current, the length of time the current flows, how long it stays in our body, how long the electrical shock is for. And next is the frequency of the current. And lastly, the pathway the current takes. So we'll go over the intensity of the current first. And let's break it down into four different range. So the current, when non-invasively applied to the skin, it can vary based on the intensity of the current. And as you can see from that graph there, there's different threshold levels, and with different threshold levels has a different physiological effect. And as you can see, the higher the current, the more severe the physiological effect is on our bodies. So with 0.9 to 1.2 milliamps, the current is just perceptible. So we could feel it, but there's not really any severe effect on our skin. Next is 15 milliamps to 20 milliamps. So with this range, it still is affecting us consistently, and the release is impossible. So that could be related to with tetany, where in this range, we're unable to let go of the wire because of our bending muscles is fixed, is contracted in that position. That's what it's referring to. And the third one is 50 milliamps to 100 milliamps. In here, it can cause ventricular fibrillation. So this could affect directly our heart, and sometimes could lead directly to death. Now with intensity of 100 milliamps to 200 milliamps, this could cause serious burns. So we spoke about this in the previous part where we discussed the different degrees of burns. And in this range, this is the one that could cause the serious burns, third, fourth degrees. And if you consider this to everyday appliances, to power a simple 25-watt lamp, we need 250 milliamps of current. And if you compare that to that range that we just spoke about, it's fairly high. Just if you just see that picture for that, to power up that lamp, it takes around 250 milliamps. So it's important to consider the safety aspects of handling these electrical appliances. That's why it's more important. It's more dangerous to handle household appliances. It's as dangerous to handle household appliances than medical equipments, because it only takes a small amount of current to actually create a physiological effect on your body in the event of an electrical shock. The next we'll talk about is time, and how does time affect the electrical current. in our body. So with time, in the initial moments of an electrical shock, the body may experience a sudden involuntary reaction. So this can include muscle contraction, sometimes violent, and potential loss of control. With prolonged exposure to electric current, this can lead to a condition known as tetany. So this is where the muscles contract and may not release. This sustained contraction can result in the affected individual being unable to let go of the source of the shock. As you can see from this graph, with between 0.1 to 0.5 milliamps is a time current graph. And the time represents on the y-axis. There's really no reaction. But you can see as we progress towards the graph, as the current increases, we slowly see reverse physiopathological effects and the probability of fibrillation and cardiac arrest. How? Because the longer the duration of the exposure of the electrical current, the greater the potential for physiological damage, as you can see from this graph. Why? Because the electric current can generate heat in tissues the longer it is there. And this could lead to the burns beneath the skin, and it could even potentially affect the internal organs. You could even have delayed onset effects. So some effects of electrical shock may not manifest immediately, but it can become apparent over time. You could sustain internal injuries like damage to organs or tissues. So time is fairly relevant as one of the factors in terms of affecting electrical current. The third one is the frequency of the current. With the frequency of the current, as you know, our body has its own harmonic frequency, and our body's frequency actually ranges from 0.5 to 100 hertz, which is why we get affected with mains frequency, because with mains frequency they operate between 50 hertz to 60 hertz. So the potential to do harm, if you're in the event of just creating a contact between us and mains, it could cause physiological effect. If you service diaphragms, why don't diaphragms cause electrical shock when applied to patients during surgeries? The reason why diaphragms don't affect us, why it doesn't cause an electric shock, is because diaphragms operate at such a high frequency. They operate between 0.5 to 3 megahertz of electrical current. This allows the diaphragm to avoid the normal human body's frequency, which prevents it from which allows the body to be unaffected during the surgery. Next is pathway. With pathway, there's different ways electrical current can travel through the body. As you can see from this picture, different pathways have different resistance. And with wet skin being the highest resistance, being the lowest resistance of all of them, which can create the most physiological effect on the body. Because with lower the resistance, the higher the current. The pathway factor in terms of electricity, it's referring to the route or the course that electric current takes through the body when a person is exposed to an electrical shock. And the pathway can significantly impact the physiological effect and the potential harm caused by electrical shock. So the pathway factor, as you can see from the right, with chest to left being the highest pathway factor, as studies have shown, there's different factors that could affect the pathway factor. So one of them is the entry and exit points. The point of entry and exit for the electrical current can determine the pathway through the body. Current may enter through one part of the body and exit through another, affecting different organs and tissues in its path. Resistance of tissues as well. Different tissues in the body offer different levels of resistance. For example, as we spoke about earlier, dry skin has a high resistance than wet skin. The resistance of tissues along the pathway affects the amount of current that flows through them. And the most dangerous pathway is if the current travels across the chest. Because if current travels across the chest, it may interfere with the heart's electrical activity, potentially leading to life-threatening conditions like ventricular fibrillation. Understanding pathway factor is crucial for assessing the potential risk and effects of electrical shock.